Hey guys, it's Landon with taughtbysurveyor.org. In this video, we're going to talk a little bit about polar coordinates. What are polar coordinates? That sounds like something that, happens in the Arctic, right? It's not. It's just a way to express or describe the location on a 2D plane. So we're going to talk a little bit about it. It's like kind of like rectangular coordinates evil twin, if you want to think about it that way. So in this video, we're going to define polar coordinate. What does that mean? We're going to talk about some metadata. Okay, now what is metadata? Metadata is data about data. That's not very helpful, right? That sounds like something the Terminator would say. Metadata, what that means is we're going to talk about some information you have to have about your polar coordinates to use them correctly. I'm going to give you an example of polar coordinates. And then we're going to talk a little bit about why and how surveyors convert from polar coordinates to rectangular coordinates and from rectangular coordinates to polar coordinates. We're not going to actually do those calculations in this video. I'll probably do another video where I show you that. Sorry, I was missing the leg of my arm there. But we're going to just kind of describe it to you in this video. Okay, so don't freak out. We're not doing any trig in this video. Don't panic. We'll save the trig for a different video. You can eat your Wheaties before you watch that one. Okay, so let's define polar coordinates. So a polar coordinate uses an angle and a distance to define the location of a single point on a 2D plane. So if you watch my other video on rectangular coordinates, you know that in a rectangular, 2D rectangular coordinate system, you use two numbers to describe a single point, right? It's usually a northing and an easting or an X and a Y. Okay, so it's a similar with polar coordinates, remember the evil twin, except we're using an angle and a distance, right? So it's angle. So you could think about it, still two numbers, but it's different kinds of numbers. In a rectangular 2D coordinate grid, both the numbers are distances or lengths. Okay, in the polar coordinate system, you only have one length. The other number that you use to describe the coordinate is an angle. Okay, so that's what a polar coordinate is. Now, we got to know some things about the angle and distance to be able to really understand the location being described by the polar coordinates. So what do we need to know? We need to know three things. This is the metadata I talked about. We need to know what's the unit of the distance. Okay, by the way, you got to know that. That's your distance unit or your linear distance unit, your linear unit. You got to know that for 2D coordinates too. You need to know the unit system and format of your anglement, anglement. That's a new word, anglement, of your angle measurement, sorry. And you also need to know what the zero direction is for the measurement of your angles. And I'll show you that. I've got a little sketch here that we're gonna look at. Okay, so three things: the distance units, the angle units, and the zero direction. All right, so let's talk for a minute before we get to our sketch here about why are polar coordinates important? Why am I teaching you this? Why is a land surveyor trying to teach you about this? Well, the reason why is pretty simple, is land surveyors frequently measure in polar coordinates. So a lot of the measuring that we do when we're out in what we call in the field, when we're outside, I guess it could be inside too, but when we're out measuring as part of our job, we are typically measuring in polar coordinates, not in rectangular coordinates. Now there could be different ways you do that. So I'm gonna give you three examples. These all produce polar coordinates. I'm going to start with the least precise and end with the most precise. So you could use a compass and a measuring wheel. Okay, that will give you polar coordinates. You could use a transit, what we call a transit, and a rag tape. Or you could use what we call a total station that measures angles and distances electronically. Okay, so all of those three types of instruments or instrument combinations, those tools, they all produce polar coordinates, not 2D coordinates. They don't produce rectangular 2D grid coordinates. They produce angles and distances. So when we're doing that kind of survey, so for example, we're surveying with a total station, which is one of the main tools we use. That total station is actually storing the raw measurement data in polar coordinates. It's angles and distances. It's not change in northing, change in easting. Now that can be calculated in the instrument, but that's not the raw measurement data that's actually stored. So what we will typically do, depending on the type of survey we're doing, is we will actually adjust the angles and distances in the polar coordinate form or format before we convert to rectangular coordinates. In other words, once you convert your polar coordinates, your measurements, your angles and distances into 2D coordinates, you lose the ability to do some types of adjustments that we like to do as surveyors because all of our measurements have a little bit of error. So we'll do, for example, what they call an angle balance or a compass adjustment or a least squares adjustment before we convert our raw measurement data into 2D rectangular coordinates. Okay, so what that means is surveyors got to be experts at this. So if you want to be a surveyor when you grow up, and of course you do, if you're watching this YouTube channel, of course you want to be a surveyor when you grow up, you need to be an expert at how to convert between polar coordinates and rectangular coordinates, and we'll talk about that in a little bit here. So let's look at just an example of a polar coordinate. So I've got a sketch here we can look at. Okay, so I've got 3 points here. I've got point 1, point 2, point 3. Okay, so just to make this help you understand this, let's just say I have an instrument, a total station set up on point 2. Okay, and I look back at point 1. That is called a back site. Okay, it's also, but you could also in this case call it like that's our baseline, our reference line, or our basis of bearings. Okay, and you got to remember one of the things we need to know, one of the pieces of metadata we need to know is the direction, the direction of the zero angle. So the zero angle direction, and I shouldn't use the degree symbol, let me use the angle symbol. Okay, in that case, it's this line right here. This defines angle. So in other words, if you're in the instrument and you turn to angle 0, literally, you can turn to angle 0 on the instrument, you're going to be looking at point 1. So that's the direction of our zero angle. In this case, in the way I've drawn it, it's due west. Okay, then you actually turn the instrument, you turn this angle, it's typically an angle to the right, because we're turning to the right. That's how most instrument, even if you turn the instrument to the left, you're measuring an angle to the right. So just imagine turning the angle to the right, and I've got a prism that we shoot the laser to, the EDM it's called, on point 3. And the instrument is going to measure this angle to the right and this distance. And I have them in purple there. So our polar coordinate would look like, let me see here. That's 90, let's call it 130 degrees. Oop. So if we're using a modern total station, we're going to get something like 130 degrees, 10 minutes, 10 seconds. That's going to be our angle. This is the angle. Okay, and then our distance, let's just say is 240 feet, 240.24 feet. That is a polar coordinate, angle and a distance. Now, you could measure another point from this same place. So we could say we're going to shoot up to another point right here. Draw another diamond. We'll call this point 4. Okay, and this is actually what we do when we're out with a total station. So this would be the polar coordinate for point number 3. Okay, so but we could have a different angle and distance that would give us the polar coordinate for point number 4. Okay, now the angle is going to be smaller because we didn't turn as far to the right. So let's just say it's 115, 50, 30. So that's our angle to the right, and our distance, it's about the same distance, a little shorter. Let's say 220, 52. Okay, those are two polar coordinates for those 2 points. We can describe those points in relation to point 2 and our zero direction, our reference line, with angles and distances, and we do that in a total station. That's how that works. Okay, so there's the example. Now I want to talk a little bit about the conversions between polar coordinates and rectangular coordinates, okay, because that's an important part of what surveyors do. Now, we're not actually going to go through those calculations. I need to do that, but I think I'm going to do it in a different video. By the way, one other thing I should explain is we're really setting up a little polar coordinate system every time we set up our instrument. Now, we use some tricks to make all the polar coordinates systems that's created at every setup of the instrument. We use some tricks to put them all on the same zero direction. So it'd be really cool if I could do an animation that would show that. I might be able to do that. I'm learning some new animation software. I'll try it because I think it would be really cool. But in essence, when you're done with your survey, even though you have little miniature unique polar coordinate systems at every setup. We rotate them all so they share the same zero direction. We merge them and we end up with one polar coordinate system for the whole survey. Okay, so let's talk about these conversions. So almost all of the drawing software that we use as surveyors and mappers, and all of the design software that our civil engineers or architects are using, that we work with, structural engineers, they almost all use rectangular coordinates. You cannot feed that kind of software typically polar coordinates. That's not how they're not made to work that way. They're made to work with 2D coordinates. So what that means is, as a land surveyor, before an architect or an engineer or a mapper can really use our measurement data, we have to convert from polar coordinates into rectangular coordinates. Now, there's some different ways you can do that. You can do it by hand. I'm going to do a video where I show you an example of that. It's painful. We don't do that in practice, but you can do it by hand. You can do it in a program like Excel. That's a little less painful, but we don't do that in Excel anymore. There's software a lot of times on the surveying instrument that will do that calculation for you. So you could do it there. You could do it in a mobile app connected to your phone if your phone will talk to your instrument. But the way we do it here, where I work at Redefined Horizons, the way most companies do it now, is we actually have special software on the desktop where we load in our raw measurement data. That's the polar coordinates, the angles and distances, with some other information. And we analyze that, do some adjustments, and then when we're done, if we've gotten rid of all the error and blunders out of our survey, then that software will convert the polar coordinates, the angles and distances, to rectangular coordinates. And then we literally export those rectangular coordinates, northings, eastings, out of our software, survey software, so they can be imported into a drawing program like AutoCAD, for example. Now, we also go the other way. Now, we don't do that as much where I work because of the type of work we do, but you also go the other way. So if you want to take 2D rectangular coordinates from a drawing, like a engineering drawing or a construction drawing, and go mark those out in the field with the total station, you actually have to convert back to polar coordinates, angles and distances, because that's what a total station works with. Now, we don't typically do that by hand. The software that's inside the total station, you give it the rectangular coordinates, the 2D rectangular coordinates, and it does the math inside the software that's on the instrument. It does the math to calculate the angle and distance that you need to locate the point from any where you're set up on the job. Now, in the old days, I want you to understand, they actually did that math by hand. So they would measure angles and distances in the field, and then they would come in. They didn't have calculators or computers. They would use a book of trig tables, and they would calculate all the change in northings, change in eastings, and they'd calculate their 2D coordinates, right? And then when they were going to go back out in the field to do layout or stakeout, they would go do that math. They'd calculate, all right, if I'm at this point and I need to stake out these 3 coordinates, what's the angles and distances that I need to turn? Now, we don't see as much of that anymore because the software does it for us, but if you're at a total station and you're doing stakeout, you can actually see, most of the time, the software that's in the instrument or the data collector will actually give you the angle and distance that you need to turn to lay the point out or stake the point out, right? So it's done the math to calculate that angle and distance, the polar coordinate. It's converted in the software, the 2D rectangular coordinate, to a polar coordinate. So we need to be able to do this as land surveyors. We need to understand what's happening. Now, what do we use? What's the tool, the math tool that we use for those conversions? It's right triangle trig. That's how you convert from rectangular coordinates to polar coordinates and from polar coordinates to rectangular coordinates. It's just simple right triangle trig. That is why you have to know right triangle trig as a land surveyor. It's a really important part of how we work, move between polar coordinates and rectangular coordinates. So if you want to be a land surveyor, you got to be good at right triangle trig, right? You need to be able to do it in your sleep. Okay, now I'm going to just give you an example. We're not going to do any actual trig, okay, but I'm going to just show you in a different color here. If we've measured this angle and distance here from point 2 to point 3, and now we want to convert to rectangular coordinates, how do we do that? I'm going to draw that in red. What we do is we figure out this change in northing. sorry, this would be change in easting. We figure out that change in easting, and we figure out that change in northing. Okay, we know this angle right here, and we know that distance. So we've got an angle and a distance. This is a right triangle. So we have a little right triangle trig problem here. We can calculate this change of easting, change in northing, and then we can calculate, if we know the coordinate for 2, we can add the change of easting, add the change of northing, and we can calculate the coordinate here for point 3. It's just a right triangle trig problem. Okay, and I'll do another video where I work an example of this. I hope I will remember to do that. There you go. There is an overview, a short overview of polar coordinates. Polar coordinates, remember, describe a location with an angle and a distance. They're really important, right? Because that's how, if you're using a total station, that's how you're storing your measurement data as a land surveyor. You're storing angles and distances. Now, the instrument, the software on the instrument or the data collector may convert to 2D rectangular coordinates, but ultimately the raw measurement is an angle and a distance. And actually, we didn't get into it in this video, but it's actually 2 angles and a slope distance. You use the vertical angle to convert your slope distance to a horizontal distance. But we'll talk about that another time. So, all right, hopefully you guys understand polar coordinates now. I'm going to do a couple more videos on 2D coordinate grids. I think I'm going to do a video. I'm going to show you how we translate all the little mini polar coordinate systems to a single polar coordinate system in a survey. And then I want to do another video where I show you kind of the basic inverse calculation on a 2D coordinate grid. And I'll do this video too, where I show you how we take the angle to the right and the distance, and we use that to come up with the coordinates for a newly measured point. We'll actually do the trig. We'll get our calculators out and we'll do the trig, okay? Thanks for watching, guys. Appreciate it.